Hello, welcome to the stream. Ooh. Do we have a fun morning planned? Oh my goodness, yes. So, got at it a little early this morning. Yeah, I just want to make sure we didn't have, 4 hours of sitting here watch me solder because, I know that's riveting. I know you all love that, but I figure, hey, maybe we'll skip that part of the fun today. And I got this pretty much assembled this morning before the stream. Hello, No Corp. Hope you're having a great Saturday. So yeah, got this mostly assembled. Literally haven't powered it on yet. Still got some wires to run. We got to jump 24 volts over here because I'm pretty sure this one's needing a jumper. But yeah, got most of the boring stuff done, so we can just focus on having a bit of fun this morning. Oh right, time zones are a thing. Well, I'm glad it was great. I'm glad your Saturday was great. Oh, I said Sunday? Oh, my bad. I'm with you. It is Sunday now. Good. Yes. So, yeah. We also got the fan monitor circuit populated. I figured we'd check that out. Oh, yeah. What we're talking about today is the battery charger. Yep. Yeah, I got that. I figured. The 0300. Yep. Got them soldered up, so we're going to run through and test them out. This one should be fun because it's got a CCCV kind of fold back mode that I jerry rigged and strapped back into the feedback pin, so that should be a lot of fun. Should be pretty interesting. Yeah. I think you've got the schematic. That's probably why you're asking. This is sheet. Is it 8 of 8? Is that right? Is it the last page? Yeah, last page of the schematic. Yes! Oh my goodness, yeah, I'm really excited. I've been looking forward to this test because it's just gonna be awesome. It's either gonna work or it won't, but either way, it's gonna be spectacular. All right. Yeah. Let's get this finished up. I didn't do any power ground checks, so I'm just gonna make sure I didn't short something critical out. 5 volts looks fine. 15 looks fine. All right, that's all probably good. Cool. So I believe we just need to jumper 24 volts over to the input and get some test points soldered in for the output, and should be about it. Yeah, this is one of those circuits where I spent a fair bit of time analyzing it back when I was doing the detailed design for this. But that was a very long time ago, so it's like I remember kind of doing the right stuff. I can't remember all the details. If we have to dig into debug, it could be interesting. Could be very interesting. That's alright, that's alright. I'm down for a challenge. Alright. I don't need test points everywhere. I'm thinking we'll want to do the 24 volt input. Yeah, and I think this is a 2 amp current limit. So I think the limit's 2 amps. Who designed this? Why did I do it? Yes, absolutely. Absolutely. I mean, thankfully, I knew that this would happen, so I left a lot of great breadcrumbs in the schematic, drew a box around it, and I'm like, this is what this does. Here is your compensation components, soft start, and disable. Oh my goodness. Thank goodness for that. Oh, other fun news. Here be dragons, that's awesome. Other fun news. So we're getting towards the end of this prototype. We've got a couple more streams based on this prototype, I think. I'm going to want to test out the PSOC 6 micro. I've been porting over the inverter controller to PSOC 6 so we can get this thing running on a proper DSP, and the performance so far looks excellent. But what I want to do is kind of strap it onto the back of our old UPS, because I mean it still works, it's just the power output's not as high as I would have liked. So we're going to strap that controller on to make sure that the voltage regulation, control loop, and all that is running just fine. Just fine. Okay, I don't really think we need any of this other stuff because this PWM input's optional right now. I've got it pre-biased to 50%, so we can just test it there and tug on it with a power supply or something if we want to. Parallel track sounds cool. Parallel track sounds cool. Oh man, I'm having one of those moments where I know that I just said something and that's a response to it, but I can't remember what it was. I was talking about the UPS feature tracks. Yeah. So yeah, once we finish that testing on the UPS and kind of strapping it together, I was reaching this point where I was like, now what? like what are we gonna do next? Oh yeah. Gotcha. Yeah, that'll be a really fun day, just because, you know, mains. Yep. Might try to push its limits. The frequency tolerance on the old design was pretty bad. I'm gonna see if I can get that dialed in on the new one. But anyways, once we're done with that, once we're done with the next couple weeks, we're in this interesting spot where I've got a lot of stuff to do, like on this prototype to actually finish it. I've got a lot of circuit analysis. I want to go back, revisit drive analysis, making sure that all the transistors are biased appropriately. I want to revisit derating and some of these things where it'll take a lot of time to go through, and it's not particularly fun to watch. And I was like, man, what are we going to make videos about? Because I need to put all this time into actually finishing the UPS so we can move forward and get to the next round of testing. And I got something. I was working on it this week, and I'm pretty excited for it. I think it's a great project because it will give me an opportunity to talk about all those fun analysis that I'm doing, but rather than doing it for a massively complex system, we can do it for something a little more simple and use it as an example to still teach the same principles, but it wasn't so much work that it's like distracting from the UPS. It's like a nice little project to make a point and walk through the analysis. And this is one of those things where I don't know if you've ever felt called to do something, but I definitely felt called to build this. And it happens to be a device, the temperature monitor for the 3D printer, because I want to make sure that I want to make sure it's actually going to work. So we had to go through and do some circuit analysis, looking at like startup transients and component tolerance, making sure that the stack up was reasonable and that the measurement tolerance on temperature was going to be sufficient to actually protect you from burning down your house. But for me, I felt called to build this thing that prevents fires if a 3D printer enters thermal runaway. And I was like, man, I don't want to ignore this in case I'm building it for me, because like we talked about last week, I much prefer my house to be not burned down. So anyways, that was fun. That's going well. So you can look forward to some more content about that in the next month or so, 2-3 weeks, something like that. We'll see what comes of it, but I think it'll be a lot of fun. Teaching principles in smaller projects, it's great. Split up the large project into smaller ones. Yeah, agreed. We've been doing this massive project, which is super cool, for a long time, but I think it'll be nice to break it down, do something a little more simple. The other thing is I've been looking into ways that we can get more cool stuff out there, and that's going to involve a PCB, so I'm going to need to order a PCB. Fun thing about the people that I've been using JLC PCB, I've had great experiences with them so far, and basically some of the PCBs I've been ordering, like these, were $2 and $15 to ship it. So I think what I'm going to do is I'm going to fix this design. I'm going to add the right amount of input and output capacitance, respin the fab, and then I'll order these, and the fixed version, and I'll add a potentiometer so you can tweak the output voltage. And then I need to make a remote temperature monitor that will end up strapping to the batteries and feed back into the battery charger circuit so we can modulate the float voltage of the lead acids with temperature. And then of course the fault tolerant temperature monitor thing. And what my plan is to find a platform where we can list those for sale, either assembled or as bags of parts. So if you guys want to get this stuff and do it at home, I'll give you guys a chance to support the channel and do something cool. And I've been looking into it, and I found a couple that look cool. JLC shipping, yeah. So I'm gonna do 3 different boards and then order it. Yeah. Yep, absolutely. Yeah, totally. So if I build more of these boards, the temperature monitor boards, and that prototype, get it all delivered, we should be in good shape, and hopefully you guys are interested in that sort of thing. Maybe we'll make some fun little EEforEveryone badges or something, LEDs. So yeah. So I guess No Corporation, you're being the most responsive in the comments, so I'll ask you. Would you want to see those things assembled, or would you be alright getting it as a bag of parts and a kit? Yeah, PCB art is always cool. Yeah, because it's a lot more effort to get these things assembled from them, to the point where something like this, I might just assemble it myself for the volumes we're going to be pushing. But yeah, I don't know. Yeah. Alright, I think we're done. Oh, right, I just wanted to check and make sure that this wasn't shorted to ground, since that's isolated right now. Should be good. Cool. So I want to check out the fan failure first, because it's easy. It'll be a nice, easy transition into our testing this morning. Cool. Fire up the scope. Not that we really need it right now. Grab us a fan. They do, but then I gotta pay for it, man. Hello, WTP Gaming. Welcome, welcome. Cool. I'm hoping this goes as well as the rest of these little circuits down here. All right, so powering on the board. LEDs are a good sign. I'm a fan of LEDs. So look at that. Can you guys see that? I don't know. I can't tell. I'm gonna zoom in. So right there, when that LED turns on, that means our... Whoa. What's going on with that? I have a feeling that one of these leads is not well soldered. Okay. Oh, sorry, that seems really out of focus. Is that better? It doesn't really look better. Come on. Oh my goodness. Could you beep a little more? What is going on? This thing is being super grumpy with me. There we go. That looks a little better. Cool. Anyways, so just gonna plug in the fan and turn it on. And so the way that this works is I should need to clear. That is not how that's supposed to work. I think I must be triggering the clear input. Okay, so the fan is spinning. And if I turn the fan off, the tack signal should stop and the error light comes on. And then once the fan is spinning again, you need to push the button to clear the error. However, it seems like something isn't quite right. I know. The thing that was getting me off, oh my goodness, making me angry, is that the multimeter and the soldering station was beeping at the same time. Just a lot of beeping. Yeah, so let's take a look at what's going on with that fan failure monitor. Could be the sense. No, that wouldn't matter. So maybe if we add a little cap from pin 3 from clear from R30 to ground, that should fix this up in a hurry. We want to go from R30 to ground. C29, is that going to ground? Yes, it is. Cool. Yeah, we can do that. Easy. Let's just put a little 0.1 mic down there. By the way, I got the new racks printed. Loving them. They hold onto the tubes a little bit tighter. So the other ones you can kind of bump it out Not a chance with these. Yeah. Yeah. Oh, honestly, no corporation. It really cracks me up when you quote me like that. Like sometimes just hearing back the thing that you said that was just ridiculous. Sometimes that's really, really funny. I'm like, yeah, now that I think about that, that doesn't really make any sense at all. Alright. Come on now. Yep. Uh-huh. That looks great. I just need a little piece of wire to tie that back. It is very interesting how sensitive that node is, but I'm pretty sure it was just floating, which is probably the problem. If we were driving that hard with a microcontroller pin, it'd probably be okay, but hey, a little bit of capacitance never hurt anyone. Or pull down, or literally anything. Man, I really didn't think about that too hard. I just kind of stole this out of the schematic. The chunk of the schematic. Yeah, so I am super pumped for all the upcoming stuff. I'm super pumped for the little mini project. I'm excited for the finishing up the CPS. And there's a lot of fun stuff happening. Okay. Oh wow. Yep. Ooh. This is pretty interesting. Man, this is like arts and crafts. Okay, almost got her. I tombstoned it a little bit just to help me. Ah! I had it! But it melted the solder on both sides of this wire. Got a little grumpy with me. Okay. It is secure. Do we... hello, Mustafa. Oh, thanks, man. I don't know about brilliant, but I certainly try really hard. So, I appreciate it. Thanks for being here. Do we low pass the soldering iron? Not sure. Not sure what you're asking there. Alright, powered it on. Fan failure detected. Clear it. I should probably do it. Does it need to change states again? Oh my goodness. No, I'm ridiculous. It's not, because it's a capacitor. It needs a resistor across it. Okay, yep, so I should have added a resistor across there as well. Alright, whatever. fact, a resistor might have been the right tool for the job all along. Okay. It's really gonna bother me if this doesn't work. So I hope you'll excuse me a moment to tack on one more component into that beautiful work of art. And then maybe I'll have to grab this, put C's in the R's. Oh my goodness. Yeah, you're gonna love this. You're gonna love this. Alright, microscope. Isn't that just a beauty? See, can I zoom out anymore? No, that's it. Yep. That is what is happening over here. That is. Oh, I'm lost. I'm lost. There it is. Oh, there's that beautiful rework. Oh, sorry. You don't think that's beautiful? Oh, you think that's ugly? Yeah. Oh, yeah, me too. Oh goodness, keep touching this switch with the soldering iron. Hunks of plastic. Alright, I think I got it. I think it's tacked down there on both sides. Yeah. Yep. Absolutely. In this case, I'm making a tower on an angle. I don't know if that's bonus points or what. But, alright, so the error was detected. Reset it. What? Oh, the fan's on. the fan was spinning. That's why we didn't detect failure. There we go. So now we got that little RC delay. Oh, look at that. Beautiful. Oh, sorry, you can't really see the LED. It's off, on, off, on. If I touch around the board, it doesn't reset because now it's not a floating input. That's beautiful. Flip the fan on, reset. Now it holds it there. Now, just as an example, if, for example, one were to stall out the fan, look at that. We detected the stall. Whoa. So, yeah. There's actually an RPM threshold, so you can see there I was just slowing it down. I didn't quite stop it, and it still tripped. So this is actually doing frequency counting. Sorry about the noise. It's doing frequency counting, and when we fall below the threshold, trips. I believe that's at the threshold to about 1,000 RPM, which is about half the RPM of this. So if we're doing PWM control, we can do 50% duty cycle. And I think this will let me do some manual PWM. Ah, come on now. Wow, that's pretty intense. But yeah, I can bypass that whole circuit. Oh. Neat. JD. Something's held for review. Oh. Sorry, JD. I really want to let that comment go. I want to let it go. It's asking me to review it. I don't know. Let's keep it positive. I saw the swear, and I appreciated it. But, you know. So this is pretty cool. Sorry, not the totally non sequitur. I like that. No Corp says, I like it when I can make the little tower. Yep. And JD says, nope, I like the install. So this is cool, because what I did is, I don't know if you can tell the difference. You probably can if I hold this up to the, here, you can hear that. So I'm going to switch this on. So this is giving it a PWM control signal of 100%. You can probably hear that's pretty loud. And when I flip it off, but I have the power jumper on and I'm doing PWM control, this just regulates down to a minimum PWM, barely a whisper. I mean, I can't hear that thing at all. So that's really cool. Unfortunately, our threshold for speed makes it trip the error. So I might have some work to do here to dial in that threshold. Play around with this a little bit, but no, I'm content. We can move on to the main event. We can move on to the main event. What do you guys think? You guys ready for the battery charger? You ready for the 50 volt nonsense? 50 volt, 2 amp, 100 watt charger? Oh yeah. I know I am. Before we do, I'm gonna make a little schematic comment telling myself, hey, add decoupling. And then that was 100k ohm pull down. I liked that combo. Excellent. Excellent. Alright, now we'll move on. So before we get super intense with loading this thing, I think I'm just going to want to check voltage regulation. Does that sound like a good place to start? Then we can hook up the scope, look at ripple, look at efficiency and whatnot. Oh, I want to spin. Do I have enough? Dope. I don't have enough cable to spin that around. Well, I guess we're keeping it this way. Oh, gotta hook over 24 volts. Alright. I might melt one of these little clips today. JD, you keep getting flagged. I'll let that one go. It's good enough. To the clip. Well, we're spitting out 2 amps at 50 volts, so that'd be 4 amps at 24. It's a pretty anemic little. We'll see. Well, we're not drawing much current. That's a good start. Let's take a look at the output voltage. No explosions. Might have worked. Might have not. Let's find out. Turn on volts. Feedback pins got 2.5 volts. That seems wrong. Output voltage has 54. That seems right. Whoo boy. That might have worked. Has anyone got the schematic handy? What am I supposed to float to? 54.00. Nice. I think that's within tolerance, because I think I've got 1%. Yeah, that's within spec. 54.3. Yep, and that's at 50% duty cycle. And so I need to take this clip here, and if I hook it onto our PWM control pin, I can simulate. So this is at 50% duty cycle right now. So first of all, yeah, we got the 54 here, and this should be 20.57 volts per volt. So 2.6 times 20.57. I don't have my calculator handy, but that seems about right. That would be what our microcontroller would see. And leaving this connected, I'm going to pull this down to 0% duty cycle, which should bump our output voltage up to 56.6. There we go. Here's a 56.8. Excellent. And if I pull that up to 5 volts, we should see 49 volts And that's our float control for temperature compensation. 51. That's a little high. You're supposed to get down to 49. Wonder if I populated a resistor wrong. Yeah, not sure. Anyways, that's looking pretty good. Let's do a little spot check on a. Well, yeah, we've got electronic load hooked up and can do all the things. Perhaps extended range above and below. Yep, absolutely. So that is that loop is going to be closed in the micro. The micro is monitoring temperature, and it's going to be driving a PWM output that'll control. I mean, we could use a DAC, but I don't think we need that. Well, I mean, I'll play around with it. If I'm not happy with the filtering that we're getting from this op amp, maybe we'll switch to a DAC, but I think it'll be alright. So I'm going to get the scope hooked up to monitor input and output voltage ripple. By the way, you guys know of any good, cheap... Yeah, that's just a resistor divider thing. So, either I miscalculated the dithering on... What would that be? That would be R170. R170, the combination of R170, 168, 167, and 166. Between all those resistors hanging off the feedback node, I think I messed up one of them. Or a couple of them. What about input? There we go. There we go. Output. Excellent. All right. Powered on. Now you can probably see that. I'll pull the DMM down. Want to run the scope. And thinking, we're doing ripple, so we want to AC couple these. By the way, if you guys have any questions about what we're doing or the lab setup or anything, shout it out in the comments. I'll do my best to respond live. No problem. All right. I'll be optimistic and set these to 100 millivolts per division. Probably going to turn on the bandwidth limit just to get rid of some of the switching noise. Whoa, wrong knob. It's looking pretty weird. Channel 2 or output ripple is looking pretty weird, but we are in super light load, so it's gonna be hard to trigger. It looks like there might be some, I don't know, the load current's so light. But what I really wanted to do here is test the enable signal. But I'm missing my DMM cookie leads. Alright, what am I seeing? YouTube is flagging the slang words. Yep, absolutely. It pops up with a little thing, JD, and it just says, "Hey, how are you sure about this? You wanna let this fly?" Yeah. And then No Corporation says, "It seems like you were about to ask about good." Oh yeah, current clamps. Current clamps. Any good cheap current clamps out there? I saw some, but none that really looked great. Thank you for keeping me on topic. because I do a terrible job of that. That's alright. That's alright. Where in the world can I get this clipped on there? That is not made for this. This is made for like clamping on a massive... Cool. We need ground. Got ground anywhere? Anywhere? Over there. This is not my cleanest lab setup. That's okay. Can't all be the cleanest. There we go, 54.33. That is our output voltage. And now if I tap the enable signal, there's no load, so it's just phew. God, I've got to discharge this massive electrolytic cap. Cool. Do I have a VNA? Yeah. I'm glad you put the emoji in there. Do you want good, or do you want cheap, or do you want bandwidth sufficient for transients? The idea would be ripple current, right? I want to pick up ripple current for the input of these power supplies, or like being able to plot the voltages and currents. This is a boost, by the way. This is a boost converter. I was especially nervous about tweaking with the feedback pin on a boost converter because I know they've got the extra pull, and I'm like, oh man, these are already more difficult to compensate than a buck. Do I really want to push my luck? Apparently yes. It seems to be okay. Alright, what am I doing? I'm getting our electronic load. Whoa! Maybe I'll turn this off, eh? The scope clips were dangling. And, oh no. Some let the smoke out. Oh, I hope it wasn't the electronic load. I hope it was one of these transistors. Something let the smoke out. Whew! Stupid! So, PSA, turn it off. Always turn it off before you start changing your test setup. I'm just gonna test the electronic load, make sure that it was something on the board that fried. Pretty sure it was one of the transistors involved with the fan power circuit. I think we shorted between two of these wires, so it might have been blasting the fan monitor with 12 volts or something. That's okay. There's a nice pop, though. What voltage is that cap rated for? Or this is rated for 60 some. I actually made a recent change because I realized it didn't have enough derating, because we're going up to like 54 volts or so, and typically want to give 20% derating on something like that. So I bumped it up to higher. There we go. Yeah, looks like the electronic load's fine. So that's good. Just blew up the fan monitor circuit. That seems fine. I don't have a VNA to cal the current probe. I'd prefer to not need to hack it. I don't need DC, but DC's alright. I wouldn't mind having DC. I'd probably prefer to have DC. Yeah, it's a 60 volt cap. 64, 65, I don't know. The new one is rated for 80 volts. 80 volts is the new one. Alright. So, from a 3-second analysis, I think we're going to be hard pressed to get this wired in the way I want to. There's a ground test point. This is being a real pain. There we go. Yes, you can get it over there. You can get this connected to the battery terminals. So this is going to be simulating, framing. There we go. This electronic load is going to be simulating our batteries for today. I'll read off the current because I can't tell if you can read that too well. But yeah, we'll get this powered on. That's the highest voltage I've ever applied to this thing. But it says it's rated for 300 and it seems fine. So yeah. Shall we? Let's do a little bit of efficiency. I've got a piece of paper here. Yeah, the thing is that the normal analyses that we would do for a power supply kind of fly out the window, because there's not much of a point in doing line and load regulation when it's got current controlled fold back. That's an irrelevant measurement. But what we could do is since we expect that current limit to be at nominally, what did I spec this at? 2.1 amps. So we could do like line regulation from 0 to 1 amp, where we'd expect the voltage to be about the same. Or sorry, line regulation is input. Sorry, load regulation from 0 to 1 amp. Then we'll do line regulation. I mean, it's a boost. That shouldn't really matter. What voltage are they calibrated for? Low, oops, seems fine. Dead shorts action should have. Yeah. I mean, for all I know, the circuit might still work. I just smelt something that sounded like a transistor exploding. Now let's see. What's the worst that could happen? I guess I could blow up a fan. Well, apparently I'm not meant to, because I set it somewhere and immediately forgot where it is. But let's do like a. What are you guys feeling for line regulation? Like 20 volts? I could try to go down to 12 volts. 12 volts to, I don't know, 30? Did I rate the input on this supply? No? Let's go to 32. What's the worst that could happen? 12 volts to 32 volts, and we'll do this at, I don't know, half an amp. Then we'll do efficiency at a 2 amp output, efficiency at a 1 amp output. Just make sure this thing's working well. And we'll kind of do a float simulation. So we'll do efficiency at like a 0.1 amp output. How's that sound to you guys? Does that sound good? Oh, you're not sure what regulation is? Awesome. Is that what that is, JD? I will be happy to explain it. So the concept of regulation is pretty simple. It's just kind of like a notation thing. Basically, there's two different types of regulation that are commonly evaluated for power supply: line and load regulation. The reason why will become obvious in just a moment. So line regulation is basically saying, we've got a regulator that's designed to make a fixed, in this case, 54 volt output. Alright, so we know we should get 54 volts out, and we're giving it 24 volts in. But now if we change our input voltage up to 30 volts, we would normally expect that the output voltage wouldn't change at all. We would expect this 54 volts to remain 54.34 volts. But usually it changes a little bit because it's not perfect. And so line regulation is a measure of how much the output voltage changes when the input voltage changes. So if we change the input voltage by 1 volt and line regulation is 1%, we would expect that the output voltage would change by 1% of the change on the input voltage, so 1% of 1 volt. Hopefully that makes sense. And then load regulation. Load regulation is kind of the same thing, only different. Sorry, I love that. I love that. By the way, is the audio good today? I had to tweak the mic volume again. Hopefully I'm not clipping or anything. Let me know if I need to tweak it. I'm right next to the EQ, so I can. But anyways, load regulation is kind of the same thing, only different, because we're not looking at the input voltage. We're fixing the input voltage to a constant level, but the output current we're changing. So we'll change from like a 0 amp load to a 1 amp load, and we'll look for how much the output voltage droops. Again, ideally, that wouldn't change at all. Ideally, it would maintain 54.34 volts no matter we were at 0 amps, 1 amp, 2 amp, but the drops, the losses within the circuit are changing, so our controller needs to compensate for that. And sometimes it can be a hint, like on these bucks, it was a hint that our output capacitance was insufficient, where we started to drop out of regulation. So even if you expect the converter to work fine, it's very good for the first time when you power it on just to run through line regulation and load regulation to make sure that the loop's working fine. And if we're looking at ripple on the scope, you might see some weird transients that might make you think it's not working right, or it might be a little unstable. So it's really useful for that. And then efficiency, as I'm sure you're familiar with, is just a more general thumb on the pulse, right? Is anything getting really hot? Are we burning a lot of power in the system? If not, we can be pretty confident that it's working well. Hopefully that was a good explanation. If not, let me know and I can revisit that. Yeah. Cool. Glad you liked it. Hopefully that helped. Alright, so we need to set this to 0.5 amp. Come on, no explosions. Oh, it's 0.7, 0.6, 0.5. Oh, that current fold back certainly does. Okay. Well, we'll still do it. We'll hold it in this DC operating point. Hey, look at that. Alright, so blue is output voltage ripple. Let's see if I can trigger on that. Woo! What am I doing? Trigger. That's what I'm doing. Channel 2, okay, so we're in the right spot. Is our level just wonky? Oh, that's a little weird. Maybe we'll try triggering on channel 1. That one looks a little more consistent. Where are we? What? Oh, channel 1. There. There we go. Looks a little better. Okay. So it looks like our output voltage ripple is kind of all over the place. That's not great. That might be a function of our current fold back. That could be a function of a few things. As a little gut check, output capacitance, inductor, input capacitance, all that is cool to the touch. As an interesting note, I held this disabled, and now we're just 23 volts. Which is... oh, that's just pulling through the diode. Yeah, that makes sense. Which would be fine, because this would be 50 volts. That would be reverse biased. That'd be okay. Alright, let me look at the comments here. Oh, I gotta scroll. Thank you guys. Dude, I love it that you guys are so engaged today. This is so cool. To go out to collect my thoughts on the current collapse. Oh, no problem, man. I'd give it a quick look and didn't see anything right off the bat, so appreciate your perspective on this. Cool. Wow. Up to the megahertz if AC only. Haven't seen any reviews on the cheap current clamps. Yeah, I know, right? I know they're like the little battery-powered jobbies that are like $50. I'm like, I don't know. I don't want to just throw it away. JD, thanks. I appreciate your brain power. Yes, indeed. Very well explained. Oh, absolutely no problem at all, JD. Absolutely no problem at all. I enjoy this a lot. AC probe is probably a DIY. Nice. Yeah? Yeah? We could probably do that. You know, honestly, Unity, I'm a big fan of them. I think they really hit a value proposition where it's like, sure, it's no fluke, but they're a decent company you can trust. Like, it might not have the best specs in the world, but I trust that their stuff meets their specs. So, I mean, that's worth something. Yeah, that's true. That's true. Used. I could probably do that. All right. Thanks for the comments, guys. I'm gonna try to do this whole regulation thing. All right. So, 24 volts in. Oh, we were gonna just hit. Oh, we are at half an amp. 24 volts in. We are at 42.9 volts out. Alright, we're gonna tweak this down. Never mind the scope freaking out, it's just the AC coupling. Gonna see if I can get this. Yeah, we're starting to drop out a little. Alright, we'll do it down to 20. Because this is a 24 volt input. Maybe I'll keep going. Let's go down to 18. That's well outside of the tolerance I would expect this thing to operate at. 18 volts in. We're at 31.8 volts out. And we're going to bump this up to a healthy 32 volts in. Whoa, something's starting to get cranky with me. Whoa, something's starting to get hot. What was that? Which one of these were getting hot? Huh? Alright, I think I'm going to limit this to 30, because this thing entered a weird operating mode above 30 volts. You can see our input current ripple went all discontinuous, like I think we're hitting a peak current limit. Which makes sense, since we're operating outside of where it was designed to operate. It makes sense we'd hit some kind of limit. So we'll leave it at 30 volts. And we're sitting at 54 volts out. That is bizarre. That is bizarre and interesting that we came back up to our float voltage. Alright. Use Tektronix and TM500 series? Gonna be expensive? I'd believe that. I could probably just look on eBay or whatever. Yeah. Perhaps a 4-channel scope and math, cheap DC current clamp. Yeah? Yeah, I mean, we've got a 4-channel scope here. So we've got plenty of channels for it. That's one of the reasons why I went 4-channel is like, man, if all you've got is 2, man, you run into that bottleneck fast. You run into that bottleneck fast. Oh yeah, I was gonna calculate what a regulation is here. Nope. Oh goodness, forgot the stream open. Okay, getting the calculator out. Getting the calculator out. So we went from 54, yikes, down to 31.8. So we dropped 22 volts on the output when we changed 30 minus. I think we might have achieved the worst line regulation I've ever measured. We have a line regulation of 185%. So we almost changed by 2 times. Oh my goodness, that is terrible. That is terrible. But like I said, this doesn't really make sense. Yeah. So I think what I'll do is let's drop this current down, because I don't really care about that. I don't really care about line regulation of something with a current. I'm worried about line regulation of our float voltage, because this needs to be within 1% of the set point at all times. So I'm just gonna tweak the input voltage a little bit. I'm gonna tweak this up to 32 volts. Now that we're at no load, we're not hitting that peak current limit. There we go. We're still at 54.35. And if I turn that down to 20 volts, now we're at 20 volts in. Look at that, 54.36. So yeah, that's what I would call good line regulation. So line regulation of the float voltage. Let me just load it for a minute and then unload it. Okay, loaded, unloaded. Yep, there you see. We're right back to 54.35. So yeah, what matters is line regulation of the float voltage, because man, if you overcharge lead acids, they'll let you know. Just by nerfing themselves. Perhaps with, yeah, or you end up with like 3 scopes running triggers between them. Yes, or that. I'd be down with that. If I could get more scopes, more better. Start like wall mounting them vertically. That'd be awesome. That'd be awesome. Yeah, okay. So really, if I'm looking at line regulation of what matters, right? I bet I can even get down to our 12 volt input. We're down to a 13 volt input. Oh my goodness, actually I'm not doing that, because at that point our gate drive is browning out. Okay, we'll keep it above 16. So our gate drive 15 volt rail can still be good. So we're at 16.3 V in. We're at 54.35 V out. Bump that up to 30. And we are at 31.4 V in. We are at 54.35 V out. That is exactly what I would expect. 0%. We did not change at all. That's perfect. Boom. All right, so we got it set back to the 24 volt nominal. Let's do load regulation from... Will you not? Yeah, well, this scope itself was the Rigol that I've got. The value proposition for this, because I've heard you can hack them and unlock features. I haven't done that, but I'm pretty sure it can be done, like protocol analyzer or whatever. But I mean, I think it was only like $100, 120 maybe for a 4-channel scope. Yeah, nothing wrong with that. Nothing wrong with that. Yeah. So we're at 0 amp output, and we're at 50. I'm sorry, what? Oh, our scope. I was like, my load is still showing me. Alright, so we're at 54.35 volts. Now let's bump up the load current. Alright. I might need to get another DMM in here. I'm starting to reach the limit of what I trust this meter to do. So this guy is going to be keeping tabs on our electronic load, because I'm trying to simulate what would be floating the batteries to make sure we can pull a little bit of current. Put this in the milliamp range. Whoa. What? This thing's unhappy with me. I don't know why. But it's super unhappy. Why is it mad? It says I'm reverse volting it. I'm not applying any voltage. There we go. Okay. Alright. So now we've got this in milliamps. Got this meter in milliamps. I'm going to try real hard to not blow the fuse out of this thing. There we go. 150 milliamps. Trying to dial this in for 100. So yeah, so we're at 100 milliamps. And we are at 54.33 volts. Let's bump this up to 200 milliamps. That's the top of this range. Oh, alright, gotta switch over to 10 amp range. There we go. 200 milliamps, we've dropped down to 43.75. Now let's just go nuts. Half an amp. Back down to 42 point, we'll call that 43. Oh, sorry, I forgot about efficiency. Back down at our approximate float. Alright, so we're getting 54.34 volts out. 54.34 times 0.1. What in the world is happening on this output? It's like our scope probe loose, and that is nuts. Actually, I wonder how much of that is the PTC fuse. Ah, stupid fuses on the output. I don't know. Maybe I'll have to bypass the fuse on this one. Ended up with some TDS 1000s for the cheap. Huh. Nice. Yeah, getting the data out, it's awesome. Oh. Oh goodness. What did I just do? Oh no, we're good. So that's how many watts out we're getting. Okay. So I'm getting hot here. It smells like something's getting hot, but I can't put my finger on it. Well, I can, but I haven't yet. Sorry, little joke. 24 volts times 0.28 amps in. We're actually running at 80% efficiency. That's not too bad. I'll give myself 81, or 80.86. Bumping up that load current. We're at half an amp. So now we're at 42.97 times half divided by 2. Taking that by our 24, we're up to 88.6% efficient at half an amp out. Getting this up to an amp. There we go. 41.72. We're seeing about, what is this, 200 millivolts a ripple? I think somewhere around there. Wow. What is going on? So I keep seeing that weird dropout, and then I'll adjust my scope probe and it goes away. I think my probe's just a little loose. We're seeing, yeah, about 300 millivolts a ripple. 300 millivolts. So we're seeing 300 millivolts on 41.66. That is 0.7% output voltage ripple. That's not too bad. Dare I say that's pretty good. Hi, Dave. Oh, no problem. Welcome, welcome. We're checking out this battery charger. It's a boost converter battery charger with a voltage fold back, and I might have blown up a fan monitor. That's about it. That's about it. You're caught up. You're caught up. Sorry you've been busy, but hopefully you had a little bit of fun. I hope you had some fun. So now we're up at 1 amp output, 41.66 times 1. Yeah, of course. Taking that, and we're dividing by our input power. I'm at 1.95. Woo! Look at us go. 89% efficient. And that output voltage ripple is still looking, you know, about 300 millivolts. Laying a laminate floor. Interesting. How'd that go? You doing that with like glue? I haven't had to lay a laminate floor before. Don't you use like construction adhesive or something? Sorry, I know, off topic. But still, I'm curious. I might be a homeowner someday. Alright, crank's up to 2 amps out. We good? Heard some crackling. That makes me nervous. Woo-wee! We're getting a little bit of heat coming out of that. Maybe some thermovias would have been a wise decision. He says now. Boom. No corporation is letting me do it. Thank you. Thank you for letting me get a little off topic. Alright, so it looks like we're... Whoa. What? What was all that noise for? This thing started making like... Well, we hit a current limit on the input. That's probably a part of it. Dang, we're pulling a lot of power through these clips. Oh wait. We're entering the land of predictable outcomes. I'm melting my clips. 1 second. Let me go get clips that won't melt. Sorry. It's hard to not laugh. Grabs anemic, tiny little clip, says, I'm probably going to melt these. Gets surprised when they start to melt. I think I stopped before it was too late. I think I saved them. I think we're good. Cool. Put that off to the side. Get a beefier. It was honestly just the clip itself. It wasn't the wire. The clip itself is just very anemic. So this should help considerably while we're tweaking this. I'm gonna put my scope around that a little better. Power it back on. Awesome. Okay, large alligator style. Was it wires or? Oh, there we go. Look at that. I didn't even read. Oh, I'm doing so good. Doing so good answering your questions. I love it. Love it when I answer questions. Okay. Alright, so we are up to where were we at? 1.5? Were we going up to 1.5? Yeah. Let's do that. 1 amp. We're seeing 41.4 volts. And 1.5, 2, and we'll see where we get the hard limit from this converter. Alright. I might want to monitor the feedback pin because I have a feeling we're getting some oscillation where we're like tripping the hard current limit and then it's turning the supply totally off and then it's turning back on and off, and I have a feeling we're getting a little bit of oscillation there. I might need to peel back the current limit just a little bit so we're current limiting to, like, you know, at 2 amps will be like a volt or something. I don't know. We'll see. Yeah. .5. 1.5 amps. We are at 40 volts on the dot. Getting up to 2 amps. What is going on? I'm hearing weird vibrations. And it's really great. So these are the same FETs we were using in the Buck. It's really great to use them in an application where, like, they're not exploding. Like, they're not bad FETs. They're pretty good FETs. It just, man, those controllers were not a good match. This controller's doing fine. It's doing fine. No problem. The inductor's cool. Everything's cool as a cucumber. 2 amps out. Now that fold back is hitting us real hard. Down to 22 volts. If there's a way to disable that on this meter, seriously, let me know. I'm fine with the turning off. Just don't beep at me. 22.2 volts. Let's see if our efficiency is falling off a cliff yet. 22.23. Come on now. Don't be like that. .24 volts in times 2 amps. 92% efficient at 2 amps out. Wow. Not bad for a diode rectified boost converter. These are actually using the same diodes as this supply. A lot of reuse. I was able to accomplish a lot of reuse overall with the bomb on this thing. So we're using same diodes, same caps, same, you know. We're not reinventing the wheel here. So just as a quick spot check. So if we're pumping out 44 watts, that means we're burning about no, there we go, burning about 4 watts in all these parts. That's not bad. The fact that that's combined between the inductor, the diode, and the FET, not to mention the quiescent draw of all the other supplies and everything else on this board, that's not bad. It's not bad. Alright, looks like I need to add a little more because our hard limit is not quite 2 amps. Whoa, we're getting 3 amps out of this thing. Whoa. What happened? Something happened. Something got not happy. Our output voltage dropped to 0, which shouldn't happen. Oh! I'm an idiot. I know what I just did. Yeah, I probably just cooked the diode. See? Because, well, I forgot that there was a diode here. So, when we hit the input voltage, when we hit 24 volts, like the 22 we were just at, that means that we're just forward biasing that diode. No, it says it's rated for 12 amps. We're probably good. So we were basically just forward biasing that D68 across the 24 volt supply. Oh, actually, that was the fuse. That was probably just the PTC blowing. Oh, I bet we're fine. I bet it just had to cool down. Boom. Hey, look at that. So yeah, it did fold back right where it should have. 2 amps. Yep. That's awesome. There's this weirdness going on. And that weirdness is right where the current limit is. I need to look at the feedback node. I think there's this weird little transient spot. You can see that on the scope. It is not pretty. Yikes! Our output voltage is all over the place! That's 5 volts per division! Yikes! Alright. So yeah, I think we might need to make it just a little bit weaker. Yeah, thanks, JD. I love it when I accidentally overload the output and it doesn't explode. Maybe we'll keep the PTC. I feel like it's doing good work right now. I'm going to switch this over to our feedback pin. Which I conveniently didn't solder a test point into. It's probably fine. Cool. Just going to... Well, I guess we're going already. Channel 1. What's going on with that? Oh, we're AC coupled. DC couple. DC couple. Okay. So this feedback node should be pretty constant throughout. Let's take a look at what's happening as that output current increases. So you can, oh, there it is. He can watch. There's our current shunt tugging. That's cool. That's really cool. So basically, we're folding back nice and linearly up to about 1.75 amps. And that's where... That's cool. I'm down for that. Yeah. What would be the minimum voltage? Save us from ourselves! Yeah, I know, right? Well, yeah, like we were saying at the beginning of the stream, No Corporation, we were joking around. It's like, who designed this thing? How does it work? What's going on? Yeah. Uh-huh. I barely remember it's a boost converter. Oh my goodness. Alright. Yeah. That FET's pretty smoking warm. But little bit of thermal via. Whoo! Hey, man. This is a little warmer than I might like, but there is no airflow. That's cool as a cucumber. Inductor's getting warm. Probably about 100 degrees. That's pretty toasty too. It's probably about 100 degrees. Maybe 150 Fahrenheit. I don't know what that is in Celsius. Yeah. What do we want to do about that? What do we want to do to fix this thing? Well, I've got a couple... Oh, right. I was going to think about the voltage on those lead acids, right? So realistically, the minimum voltage we're going to see on a lead acid, and if we see below 9 volts, that would be a problem. So we'd probably see a minimum lead acid voltage of 36 volts, which is unfortunate, because that means that this is a real scenario right here. We're seeing 37 volts and 2 amps for a sustained period of time. That's probably real. And we're pumping 73 watts into those batteries. Nice. Right, so at 0% state of charge, I'm just mapping out kind of conceptually where this is going. Can't find anything in the manual for disabling auto power off, no beep. I guess it... Yeah, I know, right? Yes! Desolder it. That is a great solution. So when our batteries are at 0% state of charge, they're going to be at about 36 volts on the terminals. And we're going to be pumping 2 amps in. Actually, let's see if I can find a technical reference manual. I've used PowerSonic batteries before, and if I remember correctly, I think they've got a great technical manual. I'm pulling up on my phone here. Let's see if I can find a document number here somewhere. I don't know. You can see that. Technical-manual PowerSonic, all one word. Alright. Wow, that is getting really hot. Alright, I'm going to peel back the current a little bit. Woo! Yeah, those need some thermal vias. That's not a very big island of copper. Maybe we'll just let that rest for a little bit. Ah, wait. Who said anything about resting? Let's find that fan. Let's get that fan hooked in. There it is. Hiding behind some wires. That is, after all, the whole purpose of cooling fans, right? Hey, look at that. I mean, there was a spark and I thought I smelled smoke, but I don't know. Seemed fine to me. Cool. Hey, look at that. Circuit board at work. Let's see if I can get this propped up somewhere reasonable. Long term, there's definitely going to be active cooling for all these circuits. So, there we go. Actually, you know what? I'm feeling kind of fancy right now. Let's do one more. Let's do one better. We needed 5 volt. We need signal. We need ground. I think there's a couple comments. I'll get to those in just one moment. Just one moment. I want to get this hooked in. I'll be there in a second. Whoa. Yep, we're good. Alright. Let's have some fun, shall we? Nice. Let's get a different color. Not feeling yellow. Green's a good color. I like green. Cool. Alright, got some comments here. Add more cooling? Yes. Yeah, this is going to be on a computer case. 2018-12? Yeah, I think so. I don't know where you're seeing a date. I'm not seeing a date on this thing. It's got like this, talks about the chemistry. But it starts talking about, there's a curve in here that I want to look at where that talks about state of charge versus battery, terminal voltage, discharge time, current, float voltage, service life. Maybe we'll just have to use the charge curve. It won't be quite right. We might need to use the charge curve. That's all right. We can use the charge curve. Okay. So as we're following this charge curve, we're going to be going up to what? Voltage per cell. So we're going to be going basically, so we're going to be stopping at 2.1 volts per cell, 2.2 volts per cell, 2.3 volts per cell, 2.4 volts per cell, and end up around like 2.45 volts per cell, right? So 2.1 volts per cell, that's really all I needed from this, and that ends up correlating to 20, 40, 60, 80% state of charge. So now coming back into the calculator here, 2.1 volts per cell, we've got 6 cells per battery, we've got 4 batteries. So that ends up being 50.4 volts. So, and that voltage gets up there pretty fast through the charging curve. 2.2. So that ends up being what? 2.2. So that would be a 52.8. 55.2. 57.6. Does that make sense? Yeah. So that would be if these batteries were very cold. We probably won't be floating that hot, but we'll just use this as an example. All right. So we're gonna get out of that constant current 2 amp mode pretty quickly. That's nice and cool. We can fire this back up. See, I've got hotkeys up the wazoo on the PC where I can actually throw stuff in the comments. And so the camera is gonna go nuts if I search for Power Sonic. I'll you know what? Let's risk it. Let's risk it. I think I can do this. Power. I knew that would happen. I knew that would happen. I knew something weird would happen. Oh right, I need technical reference manual. All right, I'm here. I'm grabbing it. Here it is. Got the link. Got the link. There we go. There it is. There's the link. That's the technical reference manual. Hopefully we're all here. Yeah. There you go. So what I want to do is figure out how long we're going to be at these incredible charge currents, because ideally we wouldn't be there very long. So when we get up to 50.4 volts per cell, wow. Yeah, once we get up to, wow, 50.4, our charge current will be pretty low. We're looking at less than 200 milliamps. Gotta be real careful with this load. Really strong. So yeah, we're at about 50.4 volts, and we'd be at 0.12 amps. That would be a nice slow trickle charge. And then up to 52.8. And just curious, I want to grab that PWM and I want to crank this up to the highest voltage I reasonably can. Come on. There we go. So our float voltage is set to a maximum right now. Alright, so at 56 volts, we're up at 0.08. So basically what this is telling me is when we've got really discharged batteries, we are going to dump 2 amps of current into them, and we're going to get them up to kind of like the float-ish area, and then this whole control circuit after probably 20-30 minutes it'll really tame itself down. Which that seems appropriate, right? We don't need to charge this super fast. Like, hopefully it'll be hours or days between power outages, but if we can get our lead acids up to 60, 70, 80% state of charge, you know, with this 1 amp, 2 amp mode. Did I trip the fuse again? What the heck? Oh, idiot. I blew the fuse in my meter. Blew the fuse in my meter. Anyways, yeah, that's my bad. Sorry, meter. So you know, we're pulling amp, 2 amps, get it up to 60, 70, 80% state of charge, then float it the rest of the way. That is the intent of the circuit. Yep, blew the milliamp fuse on the yellow one. ESR on the cells though, from what I've seen, I'm going to be dealing with SLA batteries, probably AGM, and they're looking at milliohms of internal impedance. It should be no problem to dump a couple amps in. So we're going to be targeting batteries that are rated to have about 1 kilowatt hour of capacity nominally. So just doing some rough math with you. If we're looking at about a kilowatt hour, divide that by 4 batteries. That's about 250 watt hours per battery. Divide that by the nominal voltage. We're looking at about 20 amp hour batteries. So this is a 0.1C charge for those. 0.1C, yeah, that should be. We're at a 0.1C charge rate, and you know, a couple milliwatts. But the main thing I was concerned about is these were getting uncomfortably warm. So it's like, if we're gonna be stuck in this 1 amp charge current for a really long time, I might have something to say about that. But yeah, I think we'll be good. Yeah, I don't know. I feel like we really crushed this today. We're doing good. What is this? Tune over temp? Yeah. Like, I'm feeling real good about where we're at right now. This is solid. I'm happy with the charger. I think I might keep this one. A little bit of refinement to do with that current limit, but to be honest, that's not a showstopper. What it is the problem is that I designed this so that it'll actually overtake the feedback node, but what I just did by going through the battery states is I don't think we'll ever actually hit that 2 amp. I think the voltage limit and the batteries themselves will limit the current to less than 2 amps unless they're super discharged, like almost over discharged. And we're not going to do that. We're not going to over discharge them because we're in control of that. So yeah, I don't know, that's about all I had for today. I feel like we're doing good. You guys got any questions before we call it? Definitely. Just so you guys know, Etsy is what I was looking at. They make it really easy to get on there and start like selling stuff. So we could get some EEforEveryone PCB badges up on the store. I'd want to get some stickers up on the store, and perhaps some of these buck modules, and of course the upcoming 3D printer temperature supervisor. Want to get all that up and put that on there. Oh, your meters don't have fusing? Oh boy. Oh boy. Yeah, it seems okay. Like, their fee structure is not great, but it's a lot easier than needing to like set up your own store and deal with managing payments and all that. So I figure it's kind of an open thing. There's some other platforms I've seen people use that are like very focused on DIYers, and I think Etsy's just more of a general, here's some stuff that I made. No limits other than making stuff. Yeah. So that's what I was thinking about. So you can be looking forward to that in the next couple weeks. Up on the chopping block for next week for our stream, just so you guys know, our next stream should be the backup supply. So right now, this is the charger, and this will float up. Yeah, that gets warm. That's awesome. This will float up our batteries to full charge. But when mains goes away, so does our regular DC input. So we needed a power supply that'll be able to supply the the 5 amps back to the 24-volt rail from our lead-acid batteries to keep our processing running when mains has failed. So you'll need mains to start up the system with the way I currently have it architected, because you got to feed 24 volts in through the regular input. That gets our 5, our 12, and our 15-volt rails up and running. And of course, this power supply needs the 15-volt rail to drive its FETs. So if you've got the battery voltage and you don't have anything else, unfortunately, it's not going to boot up. But yeah, it'll be able to keep itself alive. So we'll be able to rip the plug out, and yeah, that'll be pretty sweet. So we're doing this backup supply. Wide input voltage range. We're going, I think it's a regular buck, going from 50 odd volts down to something much smaller. I believe this is a synchronous guy. I believe it's synchronous, but I've also got a diode there. So, yeah, here we are. We'll be using same FETs as always. Yep, synchronous rectified, 55 volt down to 24. It'll be sweet. Yeah, seems like the comments pretty quiet. So I just want to thank you all for being here today. Thanks for hanging out in the shop and being a part of this awesome experience. I really enjoyed this. Oh, got a couple more. Been looking at resonant converter ICs. Cool. Not a whole lot. Not a whole lot of experience with resonant converters. That's one of the things I've been looking to grow into. Yeah, I've started playing around with them. I haven't had to actually tune one yet. And I feel like resonant converters are one of those things where implementing it, there's a lot of nuance, and parasitics matter a lot, especially for transformer resonant converters. I'm assuming this is a transformer resonant converter, like a zero voltage switch resonant full H or something like that. But yeah, me too. I'd love to say let's roll into it now, but there's probably like 4 hours of soldering. And by the time I solder for 4 hours, I have a feeling we'll all be bored. So I'll do that. I'll do that on my own time, and we can chat about that next week. It'll be awesome. Yeah. See you, Dave. See you, JD. Appreciate it. 2 a.m. Yeah, I feel you. Yep, just so you guys know, that next stream will be 2nd of November, so next Saturday. Same time, same place, same kind of fun. Maybe we'll have a current clamp. I don't know. The last couple streams, you've given me hints on cheap equipment, and by the time we get around to next week, I've had it. So we shall see. See you guys. See you next week.